So last day we studied about the AC equivalent circuit of a BJT network. BJT network means any network where a BJT is also an element placed in the network, and when we have to do the AC analysis, what we did, the approximation that we did is to short the capacitors. That is the first thing. Then all the DC voltages, all the DC sources were made to 0, and thereby we are in the circuits that we deal, we normally don't have current sources, we have the voltage sources. So voltage source becoming 0 means it is grounded, and when it is grounded, we see that the resistances also, the ground potential there appears at some of the resistances, so which were connected to the source previously now are connected to ground, and in that manner the entire network changes and we arrive at the AC equivalent circuit of a BJT. Now in the AC equivalent circuit, the BJT also had to be replaced by some AC equivalent model, and the first model that we are studying is the RE equivalent model of a BJT, where the resistance of the diode junction BE, that BE junction, that resistance RE, small re, is taken into the network, and we had seen that. So let us just see that once again. So this is the various common emitter and common base connection. So in the common emitter, what happens, this RE resistance is now taken to the input side multiplied by a factor beta. We know this from our previous analysis. Also here we have shown that analysis again, that the resistance, the emitter resistance is reflected to the input side scaled up by a factor of beta plus 1 actually, but in approximation we can make it as beta, and that is the thing. And RE can be very easily calculated if we get the IE current. RE is nothing but 26 millivolt by IE. So this IE is the DC bias Q point current, IE emitter current, the DC emitter current. So this we saw, and this is the AC equivalent, RE equivalent model of a BJT, of a BJT transistor. So here at the input side, we this IB current faces a beta RE resistance, and at the output side we have a current which is simply beta IB, and along with this current, so this behaves like a current source. So along with this current source, we also put a output resistance R0, which is a resistance at the CE junction basically. So this delta V CE by delta IC would give you the RO, and this is nothing but the slope of this collector characteristics. In the active region there is some slight slope, and this slope is this RO. And we came to the concept of early voltage, and we figured out that we can simply calculate it if we know what is the early voltage and what is the ICQ, the IC at the Q point. However, in going ahead in most numericals, you will see that R0 is completely neglected because this is very high and this is placed in parallel, so we can neglect this, and we don't even like get ourselves concerned for calculating the R0 in most cases. And in beta, in a common base, R0 is still higher because the slope is much flatter, and hence it can be very easily neglected. We don't bother ourselves with R0, but RE remains the same. RE has to be calculated always. So in the numericals that we will be doing for AC equivalent circuit, you have to first actually perform the DC analysis and obtain the IE current. The DC analysis you have to do before doing the AC analysis, just to get the IE at the Q point. DC analysis now you are very familiar with, you should be able to do it very easily, very quickly, and once you get the IE, you figure out what is the RE, and once you get the RE, then you replace the transistor with its AC equivalent model. You just note whether the transistor is common emitter connected or common base connected. So in common emitter, the emitter side would be grounded and the input signal would come through the base side. In common base, the base would be grounded and the input would come from the emitter side. So this is what you should note, just to identify or distinguish between what is a common emitter and a common base. There is also a common collector configuration in which the collector is grounded, but that configuration, the AC equivalent circuit remains, the RE equivalent model remains the same as the common emitter, because the input is in the base side only. So hence it remains the same. We can work with it, work with the same type of model. Now today we will start analyzing several bias configurations of these AC networks, and the first one that we are analyzing is the fixed bias. So this is a common emitter configuration. Please note this, because the emitter is grounded. Now when we have, this is the network given, this is the circuit given, and we can do the AC equivalent. What is the AC equivalent? The AC equivalent is here. Okay, so here we have shorted the capacitances, made the VCC 0, and what does it result in? So this Vi straight away comes at this point, the same point as B. This RB is starting from this point but ending in ground now. So this RB comes downwards. We can write it, we can draw it in this manner, and in the, so this is from the input side, base side. Now after that the collector end, so this C point is the same where V0 we are getting. So C and V0 remains same. Now this C is connected to RC, but this RC ends in a ground now. So this RC ends in the ground. So this, in this manner. So any doubt? Anyone trying to ask any question? Okay. So now you also note the direction of the currents. We have kept the direction of the currents as in the original circuit. So I0 here, RC is assumed to be the you can say it is as if a load resistance, but it is not a outside load. This is a load of the network. So the output current flows through this. So the output current being the IC or I0 has to flow in this branch, and we have connected a resistance here. So it behaves as a load resistance to this circuit. Now the direction, you see the direction of current is this way. So it is like pointing towards the point C. Here also we have to make it like that. So it points to the point, the current direction points to this point which is C. Okay. So in this manner. So this is I0, and similarly you can note that the direction of II input current remains same here also in the AC equivalent circuit. So the direction of the currents has to be kept same. Now this circuit can be, this is the AC equivalent circuit, but the BJT is not in a RE equivalent model. We have to change this to an RE equivalent model. Very simple. You draw this much part you draw. Here you see this much part has been first drawn. After that you have to draw the input side. input side is simply a resistance which is beta times Re. So, it will face a resistance here which is the Re resistance, but since we are reflecting this to the input side, it gets multiplied by beta. So, it is beta times Re. Now, you have to draw the output side. In the output side, there is a current which is beta Ib, the current source, and the direction of the current source obviously would be towards the base, because from here it is, you can understand that this current direction should be towards the base. So, it is towards the ground. So, this ground is the base point actually. Okay, I hope you understand. This point is the point B, capital B. Now, now you see that here you see from this point C, there has to be a resistance which is a resistance of the transistor. So, that resistance was R0, the output resistance of the transistor, that is connected here, and after that this RC comes. This RC is now connected here. Now, note also here that I0 is mentioned in the branch RC, because I0 is the current flowing through the branch RC, but after that what the current becomes here is IC. Okay. So, IC is this current. So, once we set up this equivalent network, so please ask me if there is any doubt how this particular network like became this. So, if there is any doubt in this, please ask me now. So, I hope you understood all these points, how this beta Re came in picture, how this current source came in picture, and the direction of the current source, that R0 is the output resistance of the transistor only, not the network, and after this the network's output resistance comes. And even after this, actually this Z0 and Zi are beyond. So, Z0 is the impedance seen from this point, inwards. So, it will include the RC as well as all these. Similarly, Zi will include RB and all these things. So, now we have to calculate this Zi and Z0. Remember the idea of the two-port network. Now, what we are trying to do, we are setting up a two-port. We are looking at this system now as a two-port network with the boundary of the system here. This is the boundary of the two-port network. Within this two-port network, there is the AC equivalent model of the transistor. With the AC equivalent model of the transistor, there are some input and output resistances, and that together forms the two-port network of the AC equivalent circuit. This two-port network is the two-port network of the AC equivalent circuit, the entire configuration that has been set up utilizing the BJT. So, this is the final points which you need to understand. So, now we are trying to see what would be the Zi and Z0 of this two-port network. We will always do this exercise, as we will see in later also. We will always do this exercise. Why we are doing this exercise, that will be evident a bit later, but our intention of course is to represent the entire AC bias configuration with just a simple two-port network, and that will become useful later on. When that comes, you will understand, you will appreciate it. But for this moment, we are only trying to figure out what are the Zi and Z0 of each particular network. So, here we are seeing what is Zi. You can see Zi would be Vi by Ii. That means this II is flowing through this both resistances, so these two resistances would come in parallel. These two resistances would come in parallel, and II flowing through that parallel combination is producing this drop Vi. Or another way I can say, this source Vi is causing the II current to flow through the combination of the parallel resistance of Rb and beta Re. So Zi would be Rb parallel to beta Re. Now normally this Re is in the range of ohms. This is very small, and Rb is in the range of kilo ohms, quite high. But beta is quite high also, beta is in some hundreds, but even then you will notice that in most of the circuits that you will be given to solve, your Rb is quite higher than beta Re, and we know that if we can have this Rb, one of the resistances is 10 times the other resistance, then a parallel combination is almost equal to the lower resistance. If one of the resistance is 10 times higher the other resistance, then a parallel combination can be regarded as approximately same as the lower resistance. So we only consider beta Re as the input impedance, so it is quite low. What is Z0? Remember this fact you have to remember, because you have to calculate Z0 for any circuit that you will be given. Z0 is the output impedance, and that is determined by keeping the input source, all sources are made off at the input side. So here we have the voltage source and this is made off, that means voltage source is 0. So Z0, please remember this, the output impedance of a two-port network is determined by keeping the input side voltage 0. So Vi is 0. When Vi is 0, you don't have any current flowing in these branches, so Ib is 0. So this current is also 0. This beta Ib, this current source is 0. Current source being 0 means this branch is not there, this branch becomes open circuit. Try to understand the consequences of each of these concepts, what is happening. So Ib becoming 0 means this branch is open circuit. So when you look from this side now, you only have this resistance and this resistance in parallel. There is nothing here. Okay, this is the infinite resistance. So this and this in parallel is the Z0. So Z0 is Rc parallel to R0. Normally R0 is very high, in the range of mega ohms. So it can be taken as approximately equal to Rc. I hope this is clear, the approximations, how we are calculating in output impedance. Please remember, you have to do it on your own when you are faced with a particular example. Then you have to calculate all these, you have to employ these approximations carefully, understand what these approximations mean. And even if you don't do approximations because you have calculators, you can always calculate, but still how to calculate Z0 is important to understand. When you are trying to calculate Z0, you have to set Vi as 0. This is important. Now, along with calculating the input and output impedances, we are interested in finding out another particular term for a two-port network, which is the voltage and current gains. We are talking about voltage gain here. Current gain we will actually look later on, because current gain does not come in picture when we are just having a network. Unless the load and source is connected to the network, there is no concept of current gain. So we are only looking at the voltage gain. These are the three important things we need to evaluate for each particular configuration in order to represent it as a two-port network: the input impedance, the output impedance, and the voltage gain. So this voltage gain is what? In output voltage by input voltage, that is the voltage gain. So we have to know what is the output voltage, we have to know what is the input voltage. So here the output voltage you can see. So now in this case you have everything here connected. So the input voltage is connected, you get an output voltage. Now you have to determine what is how many times the input voltage is our output voltage. So you have to connect the input voltage. So you have an input here that is giving rise to some IB, which is giving rise to this beta IB current source, and that is giving rise to some V0 output voltage. So V0 in terms of beta IB, you see this beta IB is flowing in this branch, and after this branch there is these two resistances in parallel. So the beta IB is also flowing through the parallel combination of these two, and that we already came to understand is the Z0. But here also we are not explicitly writing the Z0, but keep this in mind that it is Z0. So this is Z0, RC parallel R0 is actually Z0. We could have written Z0 also. And Vi is what? Vi, you see, Vi is this potential. So this potential is also same as beta Re into IB. So IB is the current flowing in the branch beta Re. II is the current flowing in the parallel combination of this branch. So we can take II into Zi, that is also fine. We can take IB into beta Re, that is also fine. Why we are taking IB into beta Re? Because in the output side we have been able to represent the current in terms of IB. So when we will do V0 by Vi, the current term can be cancelled. So IB becomes common and could be cancelled. But if we had taken II to formulate Vi and I0 to formulate V0, we would not have been able to establish a direct relationship between II and I0. So that's why we have taken it in this manner. So this is the reason, and we will be doing in this manner only. So please keep this in mind. So when you see the other problems also, other configurations, you will see the same repeating pattern how we are solving the network. So V0 and Vi we have obtained, and AV is simply V0 by Vi, and when you do that you simply obtain this thing by approximation that R0 is much greater than RC. So you simply get minus RC by RE. You simply get minus RC by RE. But is this RC was actually RC parallel R0, which is the Z0. Just keep this in mind. Okay, but when the R0 is not there, then RC itself is the Z0 actually. If R0 is not at all present, that means Z0 is RC only. Okay. One point to note, the 2 points to make here. One point is that this RE includes the beta. How? Remember what is RE? RE is 26 millivolt by capital IE. Capital IE is the DC emitter current, and the DC emitter current is beta times the DC base current. So the beta is there in some way in this voltage gain. So the voltage gain is getting influenced by the current gain of the transistor. So the voltage gain of the total configuration, fixed bias configuration, the voltage gain of the fixed bias configuration is influenced or is dependent on the current gain of the BJT transistor. These are some conceptual questions or maybe multiple choice type of questions which may come in your exams in future, maybe any competitive exams also. A lot of conceptual and multiple choice type of questions that could be framed from this analog electronics part. So those concepts has to be quite clear. Another thing you note, V0 and Vi are 180-degree phase shifted. How you can say this? Simply by noting that there has arrived a minus sign here. The minus sign comes from the V0. Why? Because the beta IB is in this direction. So if you consider a single resistance here, the beta IB was flowing from down to up. V0 is also from down to up. So the current direction is opposite to the actual direction it should have been because of this voltage drop. Hence a minus sign is there, and this minus sign carries over, and this indicates that the input and output voltage are 180-degree phase shifted. Now can you say whether the AV, the voltage gain, is more than 1, less than 1, or equal to 1? Normally it is more than 1 because RE would be much less than RC. RE is in ohms, RC is in kilo ohms. The next configuration is the voltage divider bias. This is also a common emitter configuration. This is voltage divider bias, so the biasing has been done in this manner, and when we do the AC equivalent circuit, now in this AC equivalent circuit directly the RE equivalent model has been placed. So it has not been drawn in two stages, it has been drawn in a single stage, and you are also advised to start practicing drawing the AC equivalent circuit in a single stage along with the RE equivalent model. Okay, so you don't need to go from here to here, then to here. You can directly come from here to here if you are practiced enough. So you can directly draw the AC equivalent model along with the RE equivalent AC equivalent circuit along with the RE equivalent model of the transistor. Now you have to be careful so that you don't do any mistake, that is the only thing. So you start from here, you see this is the point we start, the input point. So Vi, and you see the Ii and Zi are also given here. Now this point we arrive at, the B point. So this B point, from here there are two resistances R2 and R1 emerging out. R2 is also going to ground, R1 is also going to ground because VCC is now 0. So these two resistances are both going to ground. Done. And this ground point is the point E here, because this C is shorted, so RE is no more here. So this point comes up here, so this is the E point and this is the B point. So after that you have this current that is flowing. So here there would be an IB setup and it would flow through this diode junction which is giving it a resistance of RE, and if you reflect this resistance to the input side in order to make it a wholesome resistance, it would be beta RE. So beta RE resistance is there. So along with this R1 R2 there is a beta RE, and through beta RE only the IB is flowing. Please note this, that IB is flowing only through beta RE. Beyond this there are two resistances R2 and R1 in parallel, and beyond this the IE is here. So these are the only things you have to be very careful about, where are the different currents. Otherwise you will the rest of the things are quite easy. The rest of the things are only some network analysis using KVL, KCL and all that, but how to set up the network is the tricky part here, and since you are doing it for the first time you would face some difficulty, of course you will face, but when you keep looking at it, you keep doing some practice, solve some problems, things will become easier for you. So you have to do some handiwork. So do it, practice it before coming to the tutorials even, because tutorials also carry some marks. So practice it from the examples given in the book. So after this beta RE you come to the output side. So in the output side the current IC is flowing, but IC is nothing but beta IB. So this is coming inwards this side. So this current we can see show it here, beta IB, and BJT output resistance is also there, which is R0 placed here. After this, the C point emerges out. So this current IC is here in this branch, and the RO resistance is also here in this part. So here the beta IB current source along with the R0 resistance. After this, the point C comes, and after this RC resistance is there, which is connected to VCC, but VCC is now 0 here. So RC is connected to ground. And you see that I0 current is in RC branch, Z0 is looking into RC, into the C point, and V0 is the voltage at this point C. Now you have set up this AC equivalent circuit, and utilizing this AC equivalent circuit, we will be now doing the rest of the analysis. What we have to do, what you have to find out? You have to find out the parameters of the two-port network, which is formed by understanding the two-port network boundaries of the system here. This is the boundary of the two-port network for whom we are trying to figure out Zi, Z0 and the voltage gain V0 by Vi. Okay. So again we start. So this R, this is taken as R dash. This is a parallel combination, very easy to understand. This parallel combination is taken as R dashed, and then your Zi is nothing but R dashed parallel to beta Re. Please remember, in the previous configuration fixed bias, there was, in place of R1 parallel to R2, there was RB. So that RB parallel to beta Re, here it becomes R dash parallel to beta Re. Try to relate to the what you have learned previously. What are the similarities? What are the differences? This we have to identify. Only then you will learn. You will come to appreciate a new configuration, the slight differences, the distinctions. Only then you will be able to learn the subject. What is Z0? So in Z0, when we are trying to find out Z0, we have to make the Vi off. That makes this branch off, and we are seeing only RC and R0 in parallel. Again, RC R0 parallel means it is becoming RC only approximately, because R0 is quite large. So Zi Z0 found out. We have to now figure out what is the voltage gain. V0 again is represented in terms of IB, and it is simply, sorry, Vi is represented in terms of IB. It is simply IB into beta Re, and V0 is beta IB current flowing through this parallel resistance, this thing, which is RC parallel to R0. Again note that this is actually Z0. Okay, and AV is simply this divided by this, and we again get the same formula minus RC by Re. So don't assume that this is the formula which will be same always, but most of the times this is the formula that we will get. And point to make is that V0 and Vi are 180-degree phase apart. Okay. Again, is this dependent on beta or not? Yes, it is dependent on beta again. Unbypassed emitter bias. Unbypassed emitter bias means what? Previous configurations you would have noticed that there is a bypass capacitor which is placed along with the Re resistance. Along with the emitter resistance, there was a bypass capacitor placed. In this configuration, the emitter resistance is unbypassed. There is no bypass happening here. The significance of this is that when you are doing the AC equivalent circuit, emitter point doesn't become ground. There has to be a resistance connected to the emitter point, and after that the ground comes. So you see the emitter point here which was previously the common ground, but now and resistance is here, after that the ground is coming. So this is the only difference. Rest of the things you can make out now. RB is connected like this from here to ground, from base point to ground RB. Then a resistance that the input current faces, IB faces here, is small re, but that is reflected beta times in this input side, beta times RE till the emitter point. After the emitter point, this is capital RE, and after this point in the output side you see beta IB coming here, and the resistance R0 could be connected between these 2 points. R0, if R0 had to be connected, that would have connected between these 2 points, C and E, between these 2 points. But the RC is between this point and this point. RC is between C and ground. So we have not connected R0 here because R0 is quite high, and the connection of R0 would unnecessarily make analysis more complex. There is an analysis with R0 connected, which you can, for your own interest, look from the book. In the book Boylsted it is given, but Boylsted also first gives the analysis without R0, and after that it only tells you the equations, the changes in the equations that happens when R0 would be present. It doesn't go into the analysis because it becomes complex. The analysis becomes very complex. It doesn't go into the analysis. We also would not go into the analysis because R0 is quite high and we can safely ignore that. So we would analyze this network now. So to analyze this network, please note where are the Zi, Z0, Vi and V0. That is important to understand. So these are the points where your V0, Vi, Zi, V0, Z0, I0, Vi, Zi and II, these are. Okay. So now you see what is Vi. So Vi is, if you note from this branch, so we don't know what is the current in this RB. Actually we don't know this, so we don't go in this branch. We go in this branch where we have familiar currents IB, IE, and IE is nothing but beta plus 1 times IB. So in terms of IB we can represent this voltage Vi. Vi is now IB into beta RE plus this drop, which is beta plus 1 IB into R capital E. This is the R capital E. So before it was biased by the before it was bypassed by the capacitor. Now it is not bypassed. Hence this additional term comes into play. So before in the previous configurations this much was Vi. Now this additional term comes into the picture. So we have beta IB RE plus R capital E approximated. What is the approximation? This beta plus 1 is approximated as beta. Then we get this. Now what is a Zi? To know the Zi, actually we first try to understand what is a ZB, and if we can get a ZB between these 2 points, then Zi will be nothing but RB parallel to ZB. First we try to see what is the ZB. So IB we have calculated the we have got the relationship between Vi and IB. IB is the current flowing into this point, Vi is the voltage across this point. So Vi by IB would be ZB, Vi by IB would be ZB. So ZB we get by calculating Vi by IB, and from this relationship it is nothing but beta small re plus capital R. Okay. And if we employ further approximation, that this is in kilo ohms range, this is in ohms range, so we neglect the small re, so only capital Re stays. ZB becomes beta times capital Re. So Zi becomes Rb parallel to Zb. This Zb which is beta Re. Okay. What is Z0? Very simple. Z0 is nothing but Rc only. So while calculating Z0, remember we have switched off V0. So this branch is not present and hence the impedance is only Rc. Now the voltage gain Vi, what is Vi? Vi is Ib times Zb, Ib times Zb, because now we have replaced all these things, we can replace all these things with a Zb here and Ib flows through that. So Vi is nothing but Ib Zb, Zb we have already calculated as beta times Re, capital Re. V0 is what? V0 is I0 into Rc and with a minus sign because of the directions. So please note this minus sign when we are placing minus sign. When we will not be placing minus sign, there are configurations where we will not be having this minus sign. So this is your you have to be very skillful in working with the electrical networks, okay, where we are having the minus sign, where plus sign, what are the direction of the currents, all these things would be tested now when you are trying to solve these circuits. Very simple circuits, not many elements, but these things are very tricky. So unless you are used to, you might find it very difficult to face the challenge if you are doing it for the first time. So please get enough practice. I cannot stress on this further. So beta so V0, you can see V0 is minus I0 Rc. I0 is what? I0 is nothing but beta Ib, because this current is only what is flowing here. There is no current here in this branch. Please understand that there is no current in this side because no load is connected. If a load had been connected, things would have changed, but a load has not been connected. So as long as load has not been connected, this I0 is nothing but beta Ib in this case. So now the AV is what? AV V0 by Vi, and you have this Ib cancelling out, so beta Rc by Zb, and Zb is nothing but beta Re plus Re, or you can also approximate it as capital Re, which is what we have done later on. So beta also gets cancelled out and we have simply minus Rc by Re, both capital Rc, capital Re. That is, it depends on only the resistances in the network. So these are the resistances you are supplying in the network. So the gain of the entire configuration is completely in your hand, irrespective of what transistor you are using. I hope you can understand the significance of this result. The previous configurations, the voltage gain was dependent on the transistor. Now we can simply have a voltage gain of our own choice by setting the Rc and Re of our own choice. Since there is of course an approximation, but in engineering field this slight approximation does not matter. This is very less Re, and capital Re is quite high. So we can set this gain as per our choice. There is no dependence on beta. So if I ask you whether this configuration unbypassed emitter bias is the gain is dependent on beta or not, you should write it is not dependent on beta, although we know that actually in reality there is a small Re, but this can be neglected. So in engineering, so this is an engineering truth. It is not a an absolute truth actually. but it is an engineering truth. So when we are dealing in the when we are in the domain of engineering, in the domain of analog electronics, we can employ this approximation, and this approximated truth becomes the truth with which we are working. Okay, so we have someone has unmuted him or her. Who is that? Okay, so please be careful not to unmute yourself during the session, unless you have, of course, if you have a question, you are should unmute yourself, because I am not able to see your raised hand when I am teaching you here. So you should unmute straight away and ask the question, but otherwise please be careful not to unmute yourself suddenly during the session, during the class. Okay, so no dependence on beta. This is a very significant result that we have obtained with the unbypassed emitter bias. Still we are having the V0 and Vi 180 degree apart. Next one is the emitter follower, and with this I think we will end today. Yes, there are some more. So with the emitter follower we will end today. In the emitter follower also you see that the emitter resistance is unbypassed. So in the similar manner you will get this. So RB is from this point to this point. There is a beta RE and then a capital RE, then a beta IB current is flowing, and we don't have a RC resistance. We don't have a RC resistance here. Okay, and our why we don't have a RC resistance? Okay, we don't have it here, but the main point here is that the output voltage is not from the collector terminal. The output voltage is not from the collector terminal, it is from the emitter terminal. And as you can see, this collector terminal gets shorted because VCEC is ground. So this C is shorted here. So the main difference between the previous configuration and this configuration is that the output voltage is taken from the emitter point, emitter terminal, and the output current is here. I0 is flowing through RE. This is the main point of difference. When we appreciate this difference, now we can analyze in the same manner as in the previous analysis. We first try to figure out what ZB is, and ZB would be this beta RE along with this RE, and you will see that this is reflected beta plus 1 times, because this current is IE, which is beta plus 1 times IB. And doing the approximations that we have employed previously, this ZB becomes nothing but beta times capital RE. So ZI is RB parallel to this, that is ZI. Next, we have to see what is the Z0, but for Z0 actually you see Z0 is from this point. So this is a V0. V0 is not from here. V0 is from ground to emitter terminal, and we are looking into this point to see what is the Z0. So it is a bit tricky now to understand what is Z0. So what is actually done? We actually employ this thing. We try to figure out what is the IE. What is the IE in terms of Vi? Okay, so in terms of Vi, we try to see what is IE. Now IE is beta 1 times IB, which is approximated as beta times IB, and IB is nothing but Vi by ZB. IB is flowing through these branches, and the equivalent resistance is ZB. So IB is flowing through ZB. So Vi is so IB is nothing but Vi by ZB. When you establish this relationship, then replacing ZB with ZB is what? ZB is nothing but beta times RE plus small RE. We keep it here at this moment. We keep the small RE here. Why you would appreciate? You would appreciate now. So when we do this, then IE becomes VI by small RE plus capital RE. So this is almost like so this equation can be represented with this particular very simple network, very simple circuit. We have a source voltage VI. It has a source resistance small RE, which is very small, as normally source resistances are very small. We have a RE resistance capital RE, and the IE current flows through this loop, produces a output voltage across the RE resistance. The output voltage is across the RE resistance. Please see this. So this output voltage is across the RE resistance, and now the input, the impedance has to be seen from this point. Now it becomes simple for us to understand what would be the input impedance, output impedance. We simply switch off this VI to 0, and then we see that output impedance is RE parallel to small re. Output impedance is small re parallel to capital RE. So this is a major point of difference, because small re is a resistance in the input side. In the input side of the network, small re is a resistance in the input side of the network across this input, across this junction DE, which is in the input side of the network. For emitter follower, what happens? Output is not at the collector, output is at the emitter only. So this input resistance also affects the output impedance. So this input resistance RE also affects the output impedance. That is what we are seeing here. And since this small re is less than capital RE, output impedance basically becomes very much equal to RE only, small re only. This is something very peculiar about emitter follower case. Okay, please note this. And now what we have to do, we have to figure out what is the voltage gain from this same network that we have been able to draw from this equation. We can appreciate what would be V0 by Vi. It is nothing but a simple voltage divider has appeared here. So V0 is capital RE by small re plus capital RE, Vi, input voltage. So AV is nothing but capital RE by small re plus capital RE, and since small re is quite small compared to capital RE, this is almost equal to 1. This is almost equal to 1 and less than 1, of course. You note that V0 and Vi are in phase in this case. V0 and Vi are in phase. This is the first configuration where we encounter this. Vi and V0 are in phase. From this AV, the value of AV and its this phase relationship between V0 and Vi, we appreciate now why this configuration is called emitter follower. Because the emitter follows the input voltage. The emitter voltage follows the input voltage in both in phase and in magnitude very much. So if you keep your capital RE quite high, it will follow the input voltage. So here I would stop for today. We have covered a lot of configurations, starting from fixed bias, then then the voltage divider, then unbypassed, emitter bias, emitter follower, each having its own peculiarities, each being slightly different from the other, and those differences, and I have tried to point out as much as possible, but you have to figure them out yourself as well. So after the class, in the evening, I recommend you to again come back to the video, or just go to the book. You also have the PDF. Go through these configurations. Go through these configurations and try to appreciate the difference. You will also get some examples, numerical examples there, which you can practice. Okay, so I take leave now. So next class we will continue with the remaining configuration. Okay, thank you. Okay.